Hey everyone, this is me Rachit and welcome to yet another video. Few days back I had been solving few questions based on data structures and algorithms, and I found one really interesting question that I specifically want to discuss today. Now this question, I will definitely be asking this to strong candidates in interviews to test their problem solving skills. This question specifically tests whether the candidate is able to juggle between different approaches and pick up the right one, because it might happen a lot of solutions or thoughts come to your mind. To understand why your approach is wrong and which one is correct is really important, and this question beautifully tests that. The other thing is, even if you have the right approach with you, writing this down correctly is very tricky. It has good corner cases, and that's another reason why I love this problem. The third reason is that the time complexity analysis of this problem is again very good, and I strongly recommend you to try solving this problem on your own. And if you're not, I am here. I walk through the problem first and then I come up with the approach that how I'm going to solve this, and then finally I also walk you through the code and time complexity analysis. So in this video I will be demystifying this hard interview question like a pro, and I hope you learn something out of it. So we are given an array A, which is 3, 2, 5, 4, 8 in this case, and another integer S, which is 9. And now we have to tell whether we can create or reach out to some subset of A which sums to 9, but you cannot simply take any subset. There is a condition. So you have to reach a subset with some S, which is 9 in this case, using as many slicing operations you like. Now what is a slicing operation? Now slicing operation allows us to remove few elements from the array. Now slicing operations involves two steps. The first step is to take the average of min and max of array, which means if this is min and this is max, so you do an integer division of min plus max by 2, or you can say the floor value. So you take the average of min and max of array. Now the next step is you remove either all the elements of array which are less than equal to average, or you remove all the elements which are greater than average from the array. So in one slicing operation, you will basically remove either the elements which are less than equal to average or elements which are greater than average from the array. So in this way, now you have to tell me that given an array, can you make a subset which adds to 9? And you can use as many slicing operations you want. So in our example, if you will try to see, in the first slicing operation, you can see the minimum is 2 and the maximum is 8. So the average becomes 2 plus 8 by 2 integer division, which becomes 5. Now either you remove all elements which are less than equal to mid, which means you will remove all these numbers, or the other choice is you remove all the elements from the array which are greater than 5, which means this. So you can either remove these or these, but the thing is I want to make a 9, and from here I cannot make the subset sum as 9, so I'm going to ignore this and I'm going to proceed with this array. Now again, I can perform as many slicing operations I want on this one now. So that's what I'm going to do. In this case, now the minimum is 2, the maximum is 5. So the average becomes 2 plus 5 by 2. And if you perform integer division, it comes out to 3. Now you either remove all elements less than equal to 3, or you remove all elements which are greater than 3 from this array, right? So you have two choices now. Either you will reach 3, 2, or you will reach to 5, 4. In this case, since I want the subset sum to be 9 and 5, 4 is giving me, this is the answer, and I can say that yes, using few slicing operations, in this case 2 slicing operations, I can reach a subset 5, 4 in this case, which adds to given sum S. So in this case the answer is yes, and this is what the question is. The constraints for the problem, however, make this really interesting. The size of the array can be up to 100k, which is 10 to the power 5. The next constraint is the array elements can be up to 1,000,000, and the sum given S is up to 1,000,000,000,000, 10 to the power 9. The cherry on the cake is that you just don't have to solve the question for one S. You will be given multiple S. You have multiple queries, S1, S2, and so on. And you can have up to 10 to the power 5 queries. So these many questions you have to answer. And for every S1, you have to tell whether the answer is yes, no, and so on, right? So this is the problem. I will give you few time or few seconds or minutes to think about this, and then I'll be proceeding with how to approach this problem in the first place. This video is being sponsored by 𝗟𝗡𝗪, which has a collection of around 110 problems on data structures algorithms based on 14 categories. For each problem, you can see the multiple approaches and their solutions, and they also have detailed video explanations that cover time and space complexities. You can go to 𝗟𝗡𝗪𝗏.io/Rachit to check out the product. and you will also enjoy a 10% discount on your purchase. So first of all, the observation that I can make is that I can sort the array, right? And instead of subset, I can always say that I'm talking about sub array. So this can become a sub array always. And why is that? Sub array of a sorted array. So I'm going to keep my array sorted, because what's happening, like, let's try to understand that. You're having some array and then you partition it, right? You partition it and then you have, like, this is the sorted array, okay? And then you do the average of min and max, and then all the numbers, let's say, which were less than or equal to mid, they come into this area, and all the numbers which are greater than mid come into the right area. So keeping a sorted array, it makes sure that I always have this partitioning of my array into two sub arrays, which is always true. Now what is happening in one slicing operation? My array is being divided into two sub arrays, right? Not subsets, but sub arrays. And subset and sub arrays are different, right? If this is 1, 2, 3, only 1, 3 is a subset, but it's not a sub array. What I'm saying is, like, once I sort the array, I can always say that the slicing operation is dividing my array into two sub arrays, because all the elements which are less than equal to mid come here, and all the numbers which are greater than mid go over here on the right side. All right, let me clear this. Now let's say the left part is having a sum 80 and the given s was 100, right? Now you can obviously say that the answer lies in the right part, because from the left, even if you include all the numbers, it's only going to give you a max sum of 80, which means it's not going to work out. Since all the numbers are positive in the array, it's not possible that from the left, like, you cannot pick some sub array from this area which sums up to 100. So you can definitely ignore all this pile and start searching for this right part, which kind of looks like an approach, and people feel that they have cracked the main crux or the solution behind this, and they feel that they start talking to interviewer that, yeah, we are ready to write the code. But that's not going to help you. Think it like really exactly how is it going to solve the problem. Because in this case, did you think about this case where the left part, like after the first slicing operation, let's say the left part sums to 120, the right part also sums to 150, which is both are greater than 100, right? So what do you do in this case? Which part are you going to go into? Or are you going into the left, or are you going into the right? You have to think about that. And in this case, the answer can lie in anyone, right? So the next question which raises is, how do you solve this problem? If you go into both parts, what would be the time complexity of that? Like searching for a sub array in both left and right, that sums up to 100. If you keep on branching out like this for all possible partitions, so this will be a huge tree, right? So what would be the time complexity involved if you go with this strategy? So these are the kind of questions or observations that will come to your mind when you start solving this problem. But the important thing to understand over here is, when you do divide the array into two sub arrays, the interesting thing is the max minus min. Let's say if this was 200, when you do the first slicing operation, you get two parts, the left part and this is the right part. Now the interesting part is the max minus min, the max element of this left sub array and the max minus min of this right sub array. It cannot cross more than 100, because how this formed was, you did the average, right? Average was max plus min by 2. So you took the midpoint, you took the average, and that's how you got this left partitioning and right partitioning. Which means that if you do the min minus max of this, it cannot be more than 100. Similarly, if you do the min and max subtraction of this, it cannot be more than 100. So in this way, the difference between the max and min of the sub arrays, when you go after perform every slicing operation, this difference reduces by half, which means that the height of this tree can be log n at max. So just to make sure what's happening, initially the max minus min was 200, but after the first slicing operation, over here in both these left and right parts, the max minus min value cannot exceed 100. Similarly, when you go to the next slicing operations on this left part, you will get two different left and right children. And again, the difference of the max and min elements in that cannot exceed 50, right? So if you keep on going this, since it's always decreasing by the ratio of half, you can at max go down log n levels. In this case, log 2 of 200, right? So this is the maximum height of the tree, and this looks like a binary tree, which makes you feel uncomfortable because probably you are not that much comfortable solving tree questions, right? But the thing is, you got to have patience. And as we will find out, you actually do not need to implement any kind of tree in this question. But doing this analysis is really important, and I hope this is making sense so far. Now, as you have seen, like the difference kinds of like decreases by half on every level we go down. And after performing slicing operations around log 2 times, you eventually reach out this leaf node wherein the max minus min difference is just 1. What does this mean? It does not mean that this is a subarray of length 1. So this does not mean that the subarray is something like this. It might happen that the subarray is really huge, but all it's saying is that the difference between max and min is at max 1. So you can have something like 3, 3, 4, 4, 4, 4, 4. So this does not mean that the length is 1. It means that the max minus min is at max 1, right? So it can be something like this. So this kind of acts like a leaf node, or you can go one step below and it will be 0, right? Because this will be distributed into all 3s and then all 4s, right? So that's what I mean to say. The height of this tree is at max log n, which is a good news for us. And what essentially, like how essentially is this tree going to help you? Well, it's not going to help me like this, but like if you have this subarray and then you perform the mid slicing and you get 2 left and right paths. Now the thing is, if this was having some 130, it might happen that this gets broken down like this. And what I can say is that, now what can I say about this is that this sum 130 is possible, this sum 50 is also possible, and this sum 80 is also possible, right? So as I'm going down in this tree, I'm getting into different subarrays, each is having some different sum, and I can make sure that all these sums, if this is the query that you're going to ask me, then I can say yes for that. And after doing this for all the nodes in my tree, right? So if I mark all the subarray sums as true, finally, when you ask me any query, I just have to need to look into the map in which I will say that, okay, you are asking me about 65. Oh yeah, in this process down the lane, there was some subarray that was having the sum 65. So yes, the answer for this is yes. And if you ask me 72, I will say that I could not find any node in my tree and which was having a subarray sum of 72. So for 72, the answer is no. So this is the kind of intuition behind this. And you really do not need this tree structure. All you care about is these subarray sum values. So as you are making these partitions going left and right, you need to be able to, figure out the sum of this subarray and this subarray. And you need to make sure that you are storing that 50 and 80 can be a possible answer that you can get, right? So this is the process that you have to do. And to do that, what you need to do is, like if you are having some subarray, for example, 2, 3, 8, 12 and 14, right? So what do you need to make sure to go to the left and right steps? Well, first you need to compute the average, which is 2 plus 14 by 2, which evaluates out to 8, right? So this becomes your left and this becomes your right, right? So instead of storing these, like you can occupy a lot of memory if you store this, and then in the left node, you store 2, 3, 8, and then you store 12, 14, right? So instead of storing these numbers, actually, since it's a subarray, what I can instead do is I can just store the indices, which means that if this was index L to R, then I can find the, so let's call this mid. So instead of storing 2, 3, and 8, I can store simply 2 numbers, which is L and mid. And this can exactly tell me what is the subarray that I'm talking about. And over here, I can store mid plus 1 to R, right? So in this way, given L and R, I can take these two numbers, 2 and 14, compute their average, which is 8. Now for this 8, I figure out what is the index mid, which does this partition of our array, right? So I find that mid, and then I can store L mid in my left child and mid plus 1 to R in my right child. So if the array was really huge, I am not storing all these numbers in the left part, right? I'm only storing 2 numbers, which is L and the mid value, and then mid plus 1 and then R value. So I'm trying to save memory over here, if that makes sense. So, okay, this makes sense. Like you are able to go to the next slicing operation, the result of that, what is the left and right, but you also need the sum of that. right? You need to find the sum of this, which is 2 plus 3 plus 8, and you want to do this like in really fast fashion. For that, what you can do is you can store prefix sums of your array, which means that if this is 2, 3, 8, 12, and 14, you can store prefix sum, which is nothing but 2, then 2 plus 3 is 5, then 8 plus 5 is 13, then 12 plus 13 is 25, and then 25 plus 14 is 39. Now, if you want the subarray sum of something like 3 to 12, all I can do is do a subtraction of 25 with 2, right? And that will exactly, because think about this, this is having sum of this to this, and 25 is sum of this to this. So if you do a subtraction of these two, effectively this part gets cancelled out and you get the sum of this subarray in order one time, right? So you build this prefix array to get the subarray sum really fast in order one time. And then to find this mid value, like what is this index, right? To find this index, you have to do a binary search in the range L to R to figure out what is the index of this position that does this partitioning of your subarray, right? So this is done by the first number, which is greater than this average. The first number which is greater than this average is 12. And you can do a binary search because this is a sorted array, and you will get this 12 location. And you know that exactly before this you have to make the cut, and that this part will become your left area and this will become your right child. So these are the main steps involved, and I will quickly walk you through the code now. So as you can see, the code looks something like this. I am first doing the input, and finally what I'm going to do is, like, when you give me a sum s, I check in my map whether s is present. If it's present, I say yes, else I say no, right? So how do we build this map is the main crux of the problem, and we will go to that. Now, the first section is taking inputs, right? I'm taking input and then q values, and then I'm resizing my array list, and then I'm taking input of array, right? Now here is where I'm doing the sorting part, and then here is where I'm doing the prefix computation. So prefix I is nothing but the sum of current number plus prefix of I minus 1. So in this way, as we saw previously, right, this prefix sums. So this will allow us to, compute the subarray sum really fast. And we have a function for that also over here, as you can see. The sub sum from L to R is doing exactly that. If you want the sum of L to R, what I'm doing is, in prefix values, this is the sum of first R numbers, and this is the sum of first L minus 1 numbers. So if you do the difference of this and this, you exactly get the sum of L to R subarray. So for that, we have this function subsum, which takes input as L and R. Okay. And I'm using one-based indexing. For that, you have this formula right over here. Now you have done this first part of taking input. You have done the pre-computation part of prefix sums. Now here is the interesting part. What I'm doing is the initial subarray is 0 to n minus 1, right? And that's what I'm pushing into my queue. So queue is a pair of int to int. Initially, this is the subarray that you have, right? The full array. And now while queue is not empty, what I'm doing is I pick up the first element from the stack, from the queue, sorry. I pick first subarray from the queue. I know the L and R values of my current subarray, right? I find the sum of that subarray and I mark that in my map, right? Because this is a valid subarray that I can get from the slicing operations. And once I mark that, I try to go left hand child, like I try to perform a slicing operation on my current subarray, which is from L to R. So how do you compute the slicing operation and find out the next left hand child nodes? Because they will be again subarrays, right? So how do you find that? Now this is the base case, and we will come to that in a moment. So this is base case. I will come to that. But what we are doing is essentially finding out the average over here, right? So L and R, L is the smallest, R is the maximum because the array is sorted. So you find the average, and then over here you do the upper bound. And this is like, I already have a C++ STL video, which you can find out, like it has just 45 minutes, and it's a really whole deal in which you can clearly understand what is happening over here, right? So we are doing an upper bound on the array on this average value. So this gives us the next bigger element, which is bigger than average. And then I just do -1 over here so that I find out the correct mid index. So if you say your array is 1, 2, 4, 4, 5, and 7, and let's say the average over here is 1 plus 7 by 2, which becomes 4, right? So your left part is consisting of all the elements from 1 to 4 and right part is 5 to 7, right? Less than equal to 4 and greater than 4. So how do you find this index of 5? For that, I'm doing an upper bound on the value of 4. And since it's upper bound, it gives me the first number which is greater than 4, which becomes 5 in this case, right? And to come to this mid value, I do -1 over here, okay? And this, like iterators doing difference operation on a.begin, all this is covered in C++ SQL video. You will be master of that, just watch that. All right, so this is done. We find the correct mid value over here. And over here, what we are saying is if L is less than equal to mid, let's push the left subarray. And if mid plus 1 is less than equal to R, then let's push the right subarray. And that's it. You keep on, like when again this while loop occurs, you pick out the next subarray, you pop it out, you make that current sum in the map, and you try to, go further. The base case is nothing but if, like, let's say while doing this slicing operations, you get to a case where L is R. Basically, you just have one element, so you cannot perform more slice on that. Similarly, if AL and AR are same, it means that the subarray is huge, but all the entries are same, 2, 2, 2, 2, 2. So in that case also, I don't have any more slicing operation to perform. So if I do not have any slicing operation to perform, I simply do a continue, right? And that's it. Once this is done, I am like taking input of the given S, and if it exists in my map, I say yes or I say no. So I hope this makes sense, and the time complexity for this is really awesome. This is an unordered map, which means this is order 1 lookup. So this while loop is running in order Q time. Now talking about the time complexity of this while loop, this is actually kind of acting like a BFS, right? And in our tree, we will at max have around n nodes because it was a binary tree and the height of the tree was log to n, right? So the total number of nodes will be in order n. And since we are iterating on each node, that brings us the order n time complexity. However, this upper bound is a log n operation, right? And for every node, we are doing that. So that introduces an extra factor of log n, which makes the code actually n log n time. So this while loop is taking n log n time. And as an interviewer, I would really ask you about this minus operation over here, because like right now this is order 1, like you are doing difference of 2 iterators of vectors. So this is the first iterator and a.begin is the next iterator, and doing a difference on this is order 1 for vectors, but order of n in worst case for sets or maps, right? And this is again covered in our 45-minute video. Make sure to check that out. But this, as an interviewer, I would have definitely asked you the time complexity of this statement. In this case, it's still log n time because of the upper bound that you are doing, which is kind of binary search. And overall, this while loop becomes n log n as shown over here. So that's pretty much about it. And this is again normal order n loop. So the overall time complexity is dominated by n log n. And that's the correct answer. I hope you really enjoyed this problem. Let me know in comments if you were able to solve this in correct time complexity and whether you were able to figure out why your solution was wrong in the first place. I hope this was useful.
If you enjoy short written content on software engineering, make sure to follow me on LinkedIn and Twitter. For pictures, follow me on Instagram, and for programming memes, again on Instagram with the account I can't name variables. That's pretty much about it, guys. I will see you in the next one. Till then, happy coding. Bye bye.